With that being said, I just wanted to introduce my colleagues that help organize this workshop. So we have Sean Hu from the U.S. Army Research Laboratory, Ben Riggan from U.S. Army Research Laboratory, and we also had Vishal Patel from Rutgers University, who was helpful in getting this workshop set up. Unfortunately, he couldn't be here for this actual presentation. And I'm Nathan Short with Booz Allen Hamilton. So I support the Army Research Lab. I also support IARPA and a couple DHS programs across the government. So here's the agenda that we have for today. We're going to get started with an introduction of the workshop, and then we're going to have a keynote from Dr. Chris Bainan from IARPA. And then we have an invited talk from Professor Nasser Nazarbadi from West Virginia. Then we'll jump into our paper sessions. We have two paper sessions. The first one's going to be on cross-domain face recognition, so topics like sketch to photo synthesis and heterogeneous face recognition. We have a short coffee break, another invited talk from Elham Tabasi from NIST on fingerprint recognition, and then another invited talk on multispectral iris from George Quinn. And then we'll get into our second paper session on cross-domain fingerprint and iris recognition. And then hopefully we will have a Best Paper Award presentation at the end of the day presented by Polaris Sensor Technologies, and they'll give a brief overview of some of their capabilities that they have, the sensors that they build prior to announcing those awards. So what is cross-domain biometric recognition? So just a brief history. So we started this as a heterogeneous face recognition workshop. So taking face images in one imaging domain and matching them to images in another domain. So Sean's going to go into this a little bit more in detail, but examples of this are doing near infrared to visible matching, shortwave infrared to visible, thermal to visible matching. And what we're trying to do is come up with techniques that can take these images in one domain and map them, whether at the image level or the feature level, into the visible domain to provide backwards compatibility with legacy existing data sets. So we started this at Face and Gesture, I guess earlier or last summer, and we had a pretty good response from that workshop. So we did a tutorial at IJCB later in the summer, which also went well. And then thinking about it a little bit more, we kind of decided this problem isn't just unique to face recognition. There's examples in iris and also in fingerprint recognition of the same challenges. So in fingerprint recognition, you have cross-sensor issues with going from optical to capacitive. You have in iris recognition, you have different wavelengths that you can collect that where you have the same issue as we have in the face recognition domain. So what's the motivation behind this? One of the issues that my colleagues and I have specifically run into is, so we're developing new sensor capability to collect face images in low light conditions. So doing this, we're operating in the portions of the spectrum that are not traditionally captured. So these modalities provide much more distinguishing information for matching face images, but the problem is they don't lend themselves nicely to matching against visible images. And one of the main comments we always get when we're talking about this technology is, okay, well, how well does it work with the data that I already have? The data that they already have is visible face images. So we've been developing techniques to take infrared face images, match them to existing visible face images, and provide a level of performance and accuracy that folks are willing to accept. So this extends to the fingerprint domain. So we're seeing a lot more touchless technologies coming out where you don't actually put your finger on the platen, you just hold it in front of the sensor and it collects it. There's a number of benefits for this approach. The main one being is you don't have this issue with nonlinear distortions due to the skin elasticity as you're pressing against the surface of the platen. But again, it's another one of these issues where the performance suffers compared to traditional touch-to-touch fingerprint recognition. So again, this also extends to multispectral iris, where you're measuring at different wavelengths and you want to cross-compare between those wavelengths. So moving on, what do we need? We need basically this advanced sensor data to basically progress into a multimodal state or a multispectral state We need this existing data to be backwards compatible, and then once we get to a point where we are able to start recreating or collecting additional data on individuals, we can actually start exploiting some of this multimodal data from a multimodal perspective and just instead of a cross-modal perspective. So we're trying to bridge that gap to get us to the point where we can actually start using this information for more discriminative templates. So very briefly, how we set up this workshop. So we had a call for paper focusing on these different topics that I just discussed, with the key aspect being we wanted to focus on domain adaptation. So previously we had been attending the biometrics conferences. So we had a lot of good attendance from biometrics folks. What we really wanted to get to was the point where we had the machine learning and the domain adaptation communities starting to come in and at least introducing this problem to the folks researching in that space and hopefully bring some new ideas to this area. Just a quick summary. So each paper we had was reviewed by 3 reviewers. We had 6 papers selected, 3 on face, 2 on fingerprint, and 1 on iris. And we ended up with 2 paper awards. We have a best paper award and a runner-up best paper award. And just real quickly, wanted to thank our program committee for their guidance in setting up the workshop and also in helping review the papers. So we had a pretty large list of folks that helped with guidance on this workshop. So this was the opportunity for Polaris to come in and talk about some of their capabilities, so I'll do it for them. So we are working with Polaris on Biometric thermal face recognition. So if you're not familiar, this technology basically exploits the third fundamental phenomenon of light, the polarization state. So you can measure intensity, you can measure wavelength, and you can measure the polarization state. The interesting thing about the polarization state is that it has some relationship to the surface normal of the object. So in the reflected domain, it's the reflected light, and in the thermal domain where we're operating, it's the polarization state on the passive radiation from the face. So you can see here where we originally started on this problem was trying to match visible face images to thermal face images. You can see there's a large difference between these two, and what we've kind of progressed from a hardware side is now trying to take these polarimetric thermal images where you have much more detail about the face and match them to visible face images. So that's Polaris's technology. You can certainly go to their website and see more about the different sensors that they have. They have different form factors, different wavelengths that they're looking at. So with that, I'm going to jump real quickly in talking about fingerprint and cross-wavelength iris. So here are some of the issues in the fingerprint domain. So trying to do cross-sensor matching where you're taking optical, capacitive, and thermal, so different modality fingerprint images, and you're trying to match across these different fingerprints. So traditionally, in fingerprint recognition, you convert this to a binary image and extract just a point pattern where you're matching at that level. So it's not as big of a, there still are issues with cross-sensor matching. But one of the issues that I think we may run into is with the deep learning approaches, I think more texture information is going to start coming into these fingerprint templates. And the differences in these imaging domains may start to have issues when you're doing texture-based matching. So we also included latent fingerprints in this cross-domain problem, so prints that are left at a crime scene, and then also touch-to-touchless in 3D fingerprint recognition. And briefly on cross-wavelength iris, so you can collect iris images at a number of different wavelengths. There are different vendor systems collect at different wavelengths, and the performance between these different wavelengths basically, there's a loss in performance if you are trying to match iris images at one wavelength compared to one at another. And one of the main motivations behind collecting at different wavelengths is because different iris pigmentation causes the performance to drop. Specifically, with blue irises, a shorter wavelength has been better at collecting the iris texture, and then once you move into the longer wavelengths, you get better iris texture in darker brown pigmentation eyes. So that's briefly talking about finger and iris. Sean is going to come up and talk about heterogeneous face recognition, which has been the majority of our work, so kind of our expertise.
Down is forward or up is forward?
Down.
Okay. Well, thank you, Nathan. So Nathan has put a lot of work into this workshop as a lead organizer, in between working 3 jobs. Extraordinary man. But so I'll be talking about the heterogeneous face recognition work that Nathan, I, and Ben have been pursuing over the last couple of years. So basically, the definition of heterogeneous face recognition is when you try to match 2 face images from alternate imaging modalities. This is taken from Claire and Jane's paper 2013. For example, like Nathan said, if you're trying to match infrared imagery to visible imagery. Definition number 2 is identification of known persons acquired from one imaging modality using facial imagery acquired from another modality or condition. So here we're softening the definition a bit. So if you go from low resolution to high resolution matching, right, that's sort of heterogeneous face recognition as well, because typically your gallery, your databases contain usually better quality imagery than your basically the probes you're trying to match to the gallery. So in terms of across modalities, the strict definition, sketch to visible, for example, which I think Dr. Nasrabadi will be, student will be presenting, and Professor Nasrabadi will also be talking about heterogeneous face recognition as well. We have between different spectral bands in the reflective domain, for example, near infrared to visible or short wave to visible, and then we have emissive, which is mid wave to visible or long wave to visible. And of course, there's 3D, can be derived from either LiDAR or stereo, how you match against 2D imagery. The soft definition, which I mentioned before, could be resolution, temporal, such as video to still, which, different ranges, different poses, different ages. So the GNS program, has been, making a lot of headway in addressing a lot of these unconstrained face recognition problems, which we also consider as heterogeneous, right? So with respect to the DoD relevance, we want basically interoperability with existing biometric databases. So your existing databases only contain visible imagery, so whatever signatures you acquire, say at nighttime, low light conditions, using whatever imaging or sensor instrumentation, you want to be able to match it against the visible spectrum. So that's sort of been our driving motivation doing this work. So, in the interest of time, I'll not cover this in detail, but, here are some of the challenges for face recognition. Mainly in the visible domain, you have variable illumination, low resolution, off-angle pose, which is applicable to all the modalities, false detections, heavy cosmetics use. So imaging in the infrared domain, we think would complement with imaging in the visible domain, right? Providing you potentially with a 24/7 capability that's robust to variable illumination, especially in the thermal domain, and heavy cosmetics use. So since cosmetics are designed to alter your visible spectrum signature, right, your thermal signature is relatively invariant to the common types of heavy cosmetics material. And this is, I think something that Dr. Bainan will touch on in his talk as well. So in terms of the infrared spectrum, we have the visible all the way to the long wave. So visible, near infrared, and SWIR are reflection dominated. Mid wave and long wave are emission dominated. So at nighttime, right, you don't need any external illumination, right, to acquire a passive signature of a face. And Biometric is what Nathan just described. So, this sort of sets up the stage for Professor Nasrabadi's later talk. So I'll stop now and hand it over to Ben.
All right, so I guess I'm going to cover just some brief introduction to domain adaptation. So essentially, in all these problems, we're essentially trying to model the covariate shift and the changes in the data distribution. These changes could be due to different sources, as we've been talking about, the different spectra, different conditions, as Sean mentioned, but also different contexts. You could think of this as more of a computer vision problem where you have objects from different databases, and you have sort of the objects with no background versus, a very different background. So there's a lot of, contextual information there that we talk about with domain adaptation. And so I think one thing people always turn to when they hear domain adaptation is why don't you do transfer learning, especially in the deep learning setting. So the idea there is to reuse the more generic filters and the convolution neural network And then once you get to the higher levels of abstraction, you can modify those given that you have enough data to do so. So generally this works well the more similar your source and target domains are. But of course the idea is you need data to modify those higher levels of abstraction. So with domain adaptation, the idea is you're given both source and target data, but then we want to develop a model that works well in the target domain. So we generally have a lot of labeled source data, but then how do we extend that to the target domain? In the target domain, we generally assume it's either weakly labeled or even unlabeled. And so, for face recognition, you can think variable illumination, you can think visible thermal. And the idea is, we can learn a classifier for the source domain, but then once the statistics on the inputs change, we're generally going to get a drastic drop in performance. So we have to be able to facilitate this in some manner. So there's a lot of applications of domain adaptation. You can think of text recognition, where you learn a model on computer-generated digits. They're very nice and clean, but then when you try to extend it to the broader problem of handwriting recognition or even natural language processing, the problem becomes a lot more challenging. Also, there's applications in object recognition with the various backgrounds, the different data sets and whatnot, leveraging the differences in the contextual information where those objects generally are. And so if you train on one data set and then try to apply it to another, it's generally you're going to see a pretty significant drop in performance. There's also medical applications where you're trying to learn what features are useful for identifying lesions and tumors in CT imagery, but then maybe you want to apply some of that knowledge in for MRI imagery. And then lastly, we've talked about this before, there's biometric applications, which is the main idea of this workshop: iris, fingerprint, and face. And so just summarizing domain adaptation. So it's been extensively studied. It's not a new problem. There's a lot of related problems. You can think of the broader problem outside of deep learning for transfer learning. There's also multi-view learning, self-taught learning, class imbalance, the covariate shift, sample selection bias. And so a lot of approaches to deal with this. You can think of the classic problem of instance reweighting. You can model this as intermediate subspaces, semi-supervised domain adaptation, unsupervised, multi-source. So there's a lot of approaches, and so we'll look forward to hearing from the papers here shortly.